in this post from Fermat's library, it's an interesting factoid that the number of seconds or milliseconds in a day, in one full day, is the same as the fifth hyperfactorial. That is 5 to the power of 5 multiplied by 4 to the power of 4 multiplied by 3 to the power of 3 multiplied by 2 to the power of 2 multiplied by 1. So this is an actually correct statement. Now we want to find out if we can do the math ourselves and see if the numbers work out right. Let's just go here and do a expression, product of 1 to 5, apply 1 to 5, the array 1 to 5, to this expression x to the power of x. So it's going to be 1 to the power of 1 plus to the power of 1, 2 to the power of 2, 3 to the power of 3, and so forth until 5 to the power of 5. And you find the product of it. And so that happens to be 864000000. So it is the same as what they have, 864 followed by 5 zeros. So they do match. Now, can we take this further and make a general function for hyperfactorial? Instead of putting the 5 here, let's just change it to the n, to just a variable n. And we will make this into the Walrus operator for creating a function out of this, so that now we have a hyperfactorial function, and we will now use that function here for the number 5 and get the same result as what Fermat's library posting showed as the number of milliseconds in a day. So hyperfactorial is this product of k to the power of k for k varying from 1 to n. That's what the definition of hyperfactorial is. And so the series would be 1, 4, 108, 27, 648 is one number, and so forth. So let's see if, and the fifth one should be this number that we see here, the milliseconds in a day. Now let's take it one step further. So we did already define this as hyperfactorial as the product of n to n, but we can do an array on this function so that now we can provide hyperfactorial not just as up to 5 but 1 to 5. Now you see that the hyperfactorial is going from 1, 4, 108, 27, 648, and just like this one is here, and 86, 64 followed by 5 zeros. Now let's say we run this till 50. So it does run, but after some time you exceed the capacity of normal floating numbers to deal with this. So this is where we need to upgrade the expression, use big integers. So now if you come back and run this expression, you can see that it is going to give you huge set of results. Now if you do hyperfactorial of 1 to 50, you can see that the results are much bigger. Obviously it goes from 1, 4, 108, 26, 27, 648, 86, 4, 864, and followed by 5 zeros, and so on. So it obviously grows vertically, and it does give you the result from 1 to 50. As you can see, these are very, very big numbers, obviously. So you can even try to do, let's say, from 1 to 100 or something, and see how far they will go. So these are huge numbers. As you can see, ZCubes does compute at this level fairly like a power tower or something. Very beautiful. So that is the hyperfactorial session. Hope you enjoyed it. Thank you.